Welcome everybody to the second part of lecture 7. In the first part, we studied Möbius transformations and how they act on Möbius circles. We consider in particular the two types of Möbius transformation, T from C to C, a homotety. So this is a map which is linear, AZ plus B, where A and B are complex numbers such that A is different from 0. This map here is holomorphic and has also holomorphic inverse. So we have T inverse of W, which is given by W minus B over A. We also saw another Möbius transformations transforming open sets of the complex plane right at the end of the first part. This is this transformation T, which sends the unit disk D1, 0, which for this lecture we will denote simply by D, and sends this point to the upper half plane. So this is W in C with positive imaginary part. And we found a formula for this map. This map is a Möbius transformation given by minus IZ plus I divided by Z plus 1. And also in this case, one can show that this is an invertible map with holomorphic inverse. And we know how to invert Möbius transformations given the coefficients. And if we do this, we get minus W plus I over W plus I. So in both cases, we have holomorphic map, which is bijective with holomorphic inverse. And today we want to study these maps a bit better. And we give them the name of biholomorphisms. Let me give the general definition. So let's take U1 and U2 be open sets of C. Then a biholomorphism from U1 to U2 is a bijective holomorphic map F from U1 to U2 such that F inverse is also holomorphic and obviously bijective. Then we say if such a map exists that U1 and U2 are biholomorphic. So if such F exists, we say that U1 and U2 are biholomorphic. So let me make the following simple remark about biholomorphism. The first one is that F biholomorphism implies that the inverse of F is also a biholomorphism. This is basically by definition. The other thing is that if we have F from U1 to U2 and G from U2 to U3 biholomorphisms, this implies that the composition F with G from U1 to U3 is also a biholomorphism. So we can get new biholomorphism by taking compositions of ones. So now let me state the main problem we are interested in. So classifications of open sets up to biholomorphism and to describe more generally what are all the biolomorphisms between open sets. So problem, given U1, U2 open sets in C, find all biolomorphisms from U1 to U2. This is the problem we want to consider. For a very simple open set, so when U1 and U2 are equal to C, we already know actually the answer to this problem. So this is done by using an exercise we saw in worksheet 2. So if U1 is equal to C, U2 is equal to C, then F is biolomorphism if and only if F is a homotety. So this implication we saw at the beginning of this lecture, see above. And this other implication, we saw it in exercise 4, worksheet 2, where we proved that every injective map from C to C must be a polynomial of degree 1, and therefore must be a homotety. So this is already very interesting, so we can solve the problem for C. And now let me give an example of two open sets which, on the other hand, are not biolomorphic to each other. So this is C and the unit disk D are not biolomorphic. This is a very interesting result because C and D are surely homeomorphic. So we can find a continuous function from C to D which is bijective with continuous inverse, but this continuous function cannot be made to be holomorphic. So this shows a difference between continuous functions and holomorphic functions, for example, in this particular setting. Also, maybe I can write it here, although they are homeomorphic. So the proof is a nice application of Liouville's theorem. So if F from C to D is holomorphic, then what we know that F of Z lies in the disk, therefore its norm is less than 1. So this means that the function F is entire and bounded. By Liouville's theorem, F is constant. Hence, is not bijective. So this shows that these two sets are not biolomorphic. And now let me state a very deep result by Riemann that gives a very important criterion to say if two sets are biolomorphic. And this theorem works in a very particular class of sets, namely simply connected sets. So two simply connected sets U1 and U2, which are different from C, are biolomorphic. So this is Riemann's theorem. And let me now say a few words what it means to be simply connected. So here we don't have time to give a precise definition, but let's give an idea and maybe some examples. So remark, U is simply connected means, first of all, that U is connected. And the second thing is that U does not have holes and has no holes. So here, let me give an example of sets which are not simply connected by illustrating therefore what it means to have a hole. So for example, A R Z0, the annulus, this is not simply connected. Because you see here in the middle, you have this hole, which does not belong to the set. And here it is one hole, but you can think of sets with more than one hole. So more generally, I can take disk and then remove, maybe do this bigger. I can take a disk and maybe remove two disks. So I get this set here. This is also not simply connected. So here you see you have these two holes. And you can think of going on like this and give more example. What is, instead of example of simply connected sets, you have the whole complex plane C, or something which is homeomorphic to C. So also all open disks, or the region inside a contour, region inside contour, or for example, the region between two rays. So if you have here some rays starting from the origin, making angle theta, this is also gives you a simply connected region. So this is also simply connected. Very good. So these are some examples of not simply connected and simply connected sets. In particular, what we see here is that the disk is a simply connected set which is different from C. And therefore, this theorem of Riemann shows that the hypothesis of being different from C is really necessary, because we saw in this proposition here above that C and D are not biolomorphic. So this assumption here, you see, is really important. On the other hand, the theorem of Riemann shows that to solve the problem we stated here above for simply connected sets different from C, it's enough to take U1 and U2 equal to the disk. So the theorem of Riemann implies that to solve the problem stated above for U1, U2 different from C and simply connected, is enough to take U1 equal to U2 equal to D, the unit disk. Because if you 1 and U2 are not the unit disk, we know by Riemann's theorem that anyway we have a biolomorphism bringing this set to the unit disk. So what we want to know now, what are the biolomorphisms from the disk to itself? So let's give a name to this set. So we want to determine the set of so-called automorphisms of the disk. So these are biolomorphisms from the disk to itself. So these are also called automorphisms of the disk. And we will see here that Möbius transformation will help us. We need for this purpose a lemma. This is a famous lemma from Schwarz. And it goes like this. So if we have a function from D to D, which is holomorphic, and with additional property that f of 0 is equal to 0, then we know two things. The first thing is that f of z in norm is less or equal than norm of z for all points in the disk. And the second thing is that if we know that there is one point, z0, which is in the disk, but it's not 0, with the property that f of z0 in norm is actually equal to norm of z0. So if the inequality in point 1 is actually an equality at this particular z0, then if this happens, we have an angle theta in R such that f of z is a rotation of this angle theta. So if this equality between the norms is true at z0, then actually the map f is really simple. It's just a rotation by some angle. So let me give the proof in which we will use the maximum modulus principle. So the first thing we notice is that since f of 0 is equal to 0, then f of z can be written as a1 of z plus a2 of z squared. So this is the Taylor expansion at 0. And therefore, we can factor out at z and get a function g of z, which is also holomorphic, where g is a function from D to C holomorphic. Now we want to apply the maximum modulus principle to this function g. So let z be a point in D, and maybe let me already draw a picture here. So let's say we have something like this. This is my disk. And let's put now the point z somewhere here. So 0 is here, and z is there. we have to do now, we take some r, which must be a real number between the norm of z and 1. So that the r of 0 contains z. Now, the other important thing is if you want to apply the maximum modulus principle, is that we get an estimate on the norm of G at this point Z. So by maximum modulus principle, the norm of G of Z is less or equal than the maximum for theta in R or better for, let's say, W on the boundary of the disk dr0. So this is the boundary of the disk K0R of G of W. So now recall what is G. So G is F divided by Z. So this is the maximum W in this K0R of F of W divided by W. And now you see the norm of W on the circle. This is equal to R. And the norm of F is less than 1 because this circle is contained in the disk, and therefore F of K0R is contained also in the disk by assumption. So we have this inequality, and now we can take the limit for R going to 1. Take R go to 1 and find the norm of G of Z less or equal than 1. And this gives us an estimate also for F. The norm of F is then the norm of Z times the norm of G of Z. But the norm of G of Z is less than 1, so this is less or equal than the norm of Z. And we have the first part of the lemma. Now for the second part, so if Z in D minus 0 with norm of Fz0 equal to norm of Z0 holds, then this means that G at Z0 has norm equal to 1. So norm of G has a maximum in the disk, which is an open set. So by maximum modulus principle, G of Z is constant. And it must be equal to e to the I theta because the norm of G is equal to 1. And this again implies that F of Z is Z times e to the I theta, which is exactly what we had to show. Very good. So this is then the end of the proof of the lemma. And now we can use this lemma to to determine the automorphisms of the disk. So theorem 1, the automorphisms of D are exactly the Möbius transformations which preserve D. So these are transformations we considered last time. So for the proof, so for this inclusion, we saw last time. So we saw last time. So in lecture 7a. There we proved that these Möbius transformations preserve the disk and have an inverse, obviously, that also preserve the disk. So this inclusion we saw last time. So now let us prove the other inclusion. So now take F from D to D biolomorphism. We want to show that is of the type described above. So what we do, we take Z1, which is defined as the inverse image of 0. This is a point in D. So now our strategy is that we want to use Schwarz Lemma, but you see, to use Schwarz Lemma, we need a condition. The condition is that F0 is 0. First, to bring the function F to have this property here. So in order to do that, we take a point Z1, which goes to 0 when we apply F. So this is the same as saying that F of Z1 is equal to 0. And now we construct a Möbius transformation sending sending also Z1 to 0. How can this be done? So consider now T from D to D given by T of Z equal to Z minus Z1 over minus Z1 conjugate Z plus 1. So this map belongs to the automorphism group. This is exactly this first part, no? Because here you see you can just take Z0 equal to minus Z1 and you recognize this. This is one of the maps described above. So now we can take the function f theta, which is given by f composed with the inverse. And this is also an element of the automorphism group, because we know that if we compose bilomorphisms, we still get a bilomorphism. And now let's check that this f tilde satisfies the assumption of Schwarz lemma. So then f tilde of 0 is f of the inverse of 0. And this is now what? This is f of the inverse image of 0. So what's the inverse image of 0? Is the point which is sent to 0 by t. And this is the point Z1. And this, we know, is also equal to 0. Now, so here we used that T of Z1 is equals to 0, hence the inverse of 0 is equal to Z1. Okay, so now f tilde is a function which satisfies the hypothesis of Schwarz Lemma. So we apply the lemma, the first part, to f tilde. And what we get is that f tilde of Z is less or equal than norm of Z. But now f tilde is a bilomorphism, so it has also an inverse, and we can apply the lemma also to the inverse. So we apply the lemma to the inverse. And what we get is that the inverse applied to W is less or equal than the norm of W for all W. And now you see we can take as W f tilde of Z and get from this last inequality that f tilde inverse of f tilde of Z is less or equal than f tilde of Z. Okay, but the left-hand side, this is just the norm of Z. So you see, we get the norm of Z is less or equal than the norm of f tilde of Z. Before we had also that the norm of f tilde of Z was less or equal than the norm of Z. Putting these two things together, we get that the norm of f tilde of Z is actually equal to the norm of Z for all Z in D. Okay, but now we are exactly in the assumption of the lemma in the second part. So now lemma in the second part shows that f tilde of Z is a rotation, ei theta times Z. So now that we know this, we can go back to the definition of f tilde and find what is f. So therefore, what is f? F of zeta is f tilde of t of zeta. And this is ei theta times t of zeta, which is z minus z1 over minus z1 bar z plus 1. And this is exactly of the form that we saw here inside these brackets by taking z0 equal to minus z1. This is equal to I e theta times z plus z0 over z0 bar z plus 1 by taking z0 equal to minus z1. Okay, so this finishes the proof of the proposition. So we saw that here also every bilomorphism is written exactly in this way. ei theta times z plus z0 over z0 conjugate times zeta plus 1. So we determined all the bilomorphisms from D to D. This is a very interesting result because we have as a corollary that if we take two arbitrary points at 1 and W1 in D, then we can always find F, an automorphism of D, bringing the first point to the second point. So we can bring every first point to the second point, and then we can also characterize the automorphisms which fix point 0. So if we have F in the automorphism group of D, and such that F of 0 equal to 0, then F is just a rotation. So let me prove this this corollary. So for the first part, we can just take two maps. So take T1 from D to D. T1 of Z is equal to Z plus Z1 over Z1, Z plus 1. So that T1 of 0 is equal to Z1. And then we can also take a similar map for W1, take T2. T2 of Z is equal to T2 of W is equal to W plus W1, W1 bar, W plus 1, with the property that T2 of 0 is equal to W1. Then we can take F to be T2 composed with T1 inverse. This is a bilomorphism of the disk, and F of Z1 is T2 of T1 inverse of Z1. T1 inverse of Z1 is 0, and T2 of 0 is W1. So you see, we can transform every point to every other point. And in the same way, if we know that F of 0 is equal to 0, what we know about F? So we know that F is given by the formula above. So let me rewrite this as 0 equal to F of 0. According to the formula above, this is EI theta times Z, which in this case is 0, plus Z0 over Z0 bar times 0 plus 1. And you see this is equal to e to the I theta times Z0. Since e to the I theta is different from 0, this implies that Z0 must be equal to 0. And therefore, F of Z is equal to e I theta times Z. Okay, so this shows also this corollary, which opens for like an interesting question. So we know that we can send every point to every other point by using automorphisms of the disk. Is the same true for pairs of points? So if I start with a pair of points, so given a pair of points, Z1 different from Z2 in D, and another pair of points, W1 different from W2 in D, there exists F such that F of Z1 equal to W1 and F of Z2 equal to W2. So this is the question. So maybe here, does there exist? This is the question we want to answer. And we see that this is not always the case. We need a condition on the 4 points. So This is the second theorem of today. So let Z1, Z2, and W1, W2 points in D. Then there exists, let's say, T automorphism of D with T of Z1 equal to W1 and T of Z2 equal to W2, if and only if the norm of Z1 minus Z2 minus Z1 over minus Z2 conjugate Z1 plus 1 is equal to the same quantity for W1 and W2. Okay, so let me call this second equation star. And if this happens, so the map T is actually unique. So in this case, T is unique. So there is a unique map sending Z1 and Z2 to W1 and W2, provided this equation star hold. Okay, so let me give a proof of this statement. So we have to prove two implications. Let's start with this implication. So we assume that the equation star hold. So if equation star holds, then there exists some e to the I theta, a number of modulus 1, such that W2 minus W1 over minus W2 conjugate W1 plus 1 is equal to the EI theta times Z2 minus Z1 minus Z2 conjugate Z1 plus 1. Now, because the two numbers have the same norm, so there exists some rotation bringing one to the other. And let me call this second equation here star star. So now the idea is define, given the equation star star, this gives us a way to define three Möbius transformations. So define the following three Möbius transformations, T1, T2, and S, which is Möbius transformation preserving the disk. So T1 is the transformation Z minus Z1 over minus yeah, so here I think I made a small mistake in the conjugate. So the conjugate should go to Z1 and W1. And the same here below. So Z1, Z2. Okay, so now it's correct. So, right, so now this is minus Z1 bar, Z plus 1. And T2 is the same thing for W. So T2 of W is W minus W1 over minus W1 bar W plus 1. And the last is S, which is the rotation by angle, e to the I theta. Very good. So now this equation star star suggests that we take T to be T1 composed with S composed with T2 inverse. So this is also an element of the automorphism group. And let's see that this is the element that we want. So happens to T of Z1. This is T2 inverse of S of T1 of Z1. So let's look what happens to that Z1 under T1. Z1 is sent to 0. So we get T2 inverse of e to the I theta times 0. And this is again T2 inverse of 0. And now if we look at what T2 does, the inverse of T2 brings 0 to W1. Because again, T2 of W1 is equal to 0. So the first point goes to the first point. We are happy. So let's see that also the second point goes to the second point. So we observe that T of Z2 equal to W2. This is equivalent to the fact that T2 inverse of S of T1 of Z2 is equal to W2. I just rewrote T. And now I can apply T2 on both sides, and I get S of T1 of Z2 equal to T2 of W2. And this equation is just the equation above, because the right-hand side is W2 minus W1 over minus W1 conjugate W2 plus 1. So here I still introduced this mistake. And on this other side, we get the EI theta times Z2 minus Z1 over minus Z1 bar Z2 plus 1. Okay, so this is then exactly the equation star star, which we know it's true. Okay, so this is then this implication. Let's do the reverse implication. So in this reverse implication, now we know we have T sending Z1 to W1 and Z2 to W2. And now we consider S, which is defined as the function as we had before S. So this S is T1 inverse and T2, where T1 and T2 are defined as above. So the idea now is that we want to show that this S so defined is a rotation. How do we do this? We just need to check that S is fixing the 0. So we check that S of 0 is T2 of T of T1 inverse of 0. So T1 inverse of 0 is Z1. T of Z1 is W1 by definition. And T2 of W1 is equal to 0. So S0 is equal to 0. This means that S of Z tilde is equal to e to the I theta times Z tilde. Very good. So we have what? We have that the equation e to the I theta times T1 of Z2. So this is equal to S of T1 of Z2. And this is equal to T2 of T of Z2. Because here we exploit the fact that S is equal to T2, T1 inverse. And now T of Z2 is W2, so we get T2 of W2. This means that e to the I theta is equal to T2 of W2 over T1 of Z2. And this means two things. So the first thing is that the norm of T2 W2 is equal to the norm of T1 Z2. And this is exactly the equation star. And the other thing is that theta is uniquely, or e to the I theta more precisely, is uniquely determined by Z1, Z2, W1, W2. So it does not depend on the map T. And T, which is given by T2 inverse S T1, is unique since S, which was given by e to the I theta times Z tilde, determined only by Z1, Z2, W1, W2. Okay, so you see, we wrote T as a composition of maps, which depends only on Z1, Z2, W1, W2. Therefore, T is unique. So we don't have any choice. It's given by the formula shown above. Very good. So this proved the theorem 2. And actually, I want to finish the lecture with a final remark, which is not relevant for the exam, but maybe gives you some ideas for a possible project or thesis as a follow-up. So let me make this final remark, which is not relevant for the exam. Is that what we show here is that we can define this function delta Z1, Z2, which is the function given by this equation star. Z2 minus Z1 over 1 minus Z2, Z1 bar. So this function here can be used to define the hyperbolic distance in the following way. The hyperbolic distance between Z1 and Z2 is twice the arctangent hyperbolicus of delta. And this is a distance between points Z1 and Z2 in the disk. So we get a notion of distance, which is different from the notion of Euclidean distance. But still, this is, one can show this is a distance function. So we can show that the hyperbolic satisfies three properties, or yeah, the properties more generally, I don't know here your exact definition of distance function, but so it has to be symmetric, satisfy the triangular inequality, and must be 0 exactly when z1 is equal to z2, the properties of a distance function. And then what you see is that theorem 2 implies that if you have an automorphism of D, preserves the hyperbolic distance. So this means that if you take the hyperbolic distance between image of 2 points, is the same as the hyperbolic distance of the original points. So you can think that these automorphisms are a bit like isometries for Euclidean geometry. So in Euclidean geometry, isometries preserve distances. In the same way, these automorphisms of the disk preserve the hyperbolic distance, which is a new type of distance, giving you a new type of geometry. So this yields a new type of geometry. It's a hyperbolic one. So different from Euclidean. In particular, what are the lines in this geometry? And here we come back to the notion of Möbius circles. Hyperbolic lines are given by C intersected with the disk, where C is a Möbius circle orthogonal to the boundary of D, so orthogonal to K0, 1. So let me maybe draw an example. So here you have the hyperbolic, the unit disk, this is D. And then your Möbius circles have to be orthogonal to the boundary of the disk. So this is, for example, a line passing through the center. Or you have also other types of circles like this. This is also a hyperbolic line. Or you can now think something in this direction here. This is also a hyperbolic line. And here in the middle, you see you get hyperbolic triangle. So this is a hyperbolic triangle. And in this geometry, which is very different from the Euclidean one, for example, you can show that if you take the interior angles of this triangle, then the sum of these angles is not pi like in the Euclidean case, but it's strictly less than pi. So this is very interesting because it gives you another model of geometry where, for example, you have many lines which don't intersect each other. So for example, I can draw all the lines like this, and then these are all lines which are in some sense parallel to each other because they don't intersect. Intersect each other. And this is an example of a property that is different from the Euclidean one, because if you fix now a point here, you know that you can find many parallel lines which don't intersect this given, for example, blue line. So there is not only one parallel line through any point which doesn't belong to the blue line. So the blue line has many parallel lines through the point Z. On Z is this point here. This is also another property which is very different from the Euclidean one. Okay, thank you for the attention.